안녕하세요, 여러분. 2022 이온큐 큐센터 퀀텀챌린지에 대해서 간단히 소개를 해드리려고 합니다. 저희가 이 작년에도 이 이벤트를 진행을 했었는데요. 많은 참가자들이 이온큐 양자 컴퓨터를 사용을 해보면서 좋은 시간을 가졌던 것 같습니다. 올해도 이 이벤트가 시작을 하니까 많이 참여를 부탁드리고요. 이벤트에 대한 간단한 설명을 드리도록 하겠습니다. 예, 이벤트 개요는 다음과 같습니다. 이 이벤트는 이온큐 사이언티스트들이 제시한 양자 컴퓨팅 관련 문제들을 여러분들이 주어진 기간 동안 해결을 하는 이벤트고요. 여러분들이 이온큐 양자 컴퓨터를 직접 활용을 해보실 수 있고, 또 이를 통해서 양자 컴퓨팅을 배우고 더 잘 이해할 수 있는 기회라고 생각을 합니다. 참가 자격과 방법은 다음과 같습니다. 우선 국내 대학 소속의 대학생 또는 대학원생, 개인 또는 2인 이하의 팀이면 모두 다 참가가 가능합니다. 3명 이상의 팀은 만드실 수가 없고요. 팀으로 만드실 경우엔 2명까지 혹은 개인 단위의 참가도 가능합니다. 참가를 하고 싶으신 분들은 퀀텀 챌린지 홈페이지에 들어가셔서 온라인으로 접수를 해주시고요. 이 접수 절차가 이온큐 클라우드 사용을 위해서 필수적이기 때문에 반드시 시작을 하시기 전에 접수를 먼저 해주시기 바랍니다. 이벤트 진행 방법은 다음과 같습니다. 총 3가지 문제가 공개될 예정이고요. 문제 1번은 베리에이셔널 아이겐솔버에 관련된 문제. 문제 2번은 퀀텀 GAN, 제너레이티브 네트워크에 관련된 문제입니다. 3번째 문제는 아직 준비 중에 있고요. 준비가 된 대로 공개를 하도록 하겠습니다. 그래서 여러분은 낮은 레벨의 문제부터 순서대로 풀어야 하며 원하는 문제를 원하는 레벨까지 풀어서 제출을 하시면 됩니다. 각 문제는 레벨 3까지 준비가 되어 있고요. 레벨 1에서 레벨 3로 갈수록 점점 어려워집니다. 여러분은 레벨 1, 레벨 2, 레벨 3를 단계적으로 푸시면서 푼 만큼 제출을 해주시면 되고요. 레벨 1까지만 풀었더라도 제출을 해주시면 그거에 대해서 저희가 평가를 하고 맞게 푸신 분들에 대해서 저희가 발표 및 프라이즈를 지급하게 되었습니다. 제출 시 유의사항은 다음과 같습니다. 심사위원이 코드를 실행하기 위해서 덕후 파일 형태로 제출을 하는 것을 권장합니다. 작년 이벤트에서 이 부분은 피드백이 많았던 부분이기 때문에 반드시 모든 디펜던시를 포함한 도커 파일의 형태로 제출을 하시고요. 만약 도커에 익숙하지 않으시면은 기존에 하시던 대로 주피터 노트북 형태로 제출도 가능합니다. 다만 이때는 모든 디펜던시가 포함이 되어 있어야 하며 심사위원이 이 주피터 노트북 파일만으로 코드 실행에 실패할 경우에는 채점하지 않도록 하겠습니다. 그러므로 모든 주피터 파일 노트북에 맨 첫 번째 부분에 필요한 디펜던시, 필요한 라이브러리들을 모두 직접 설치를 하는 코드를 넣어주시기 바랍니다. 이를 위해서는 제출 전에 반드시 새로운 파이썬 환경을 직접 만드시고 여기서 노트북을 실행을 해서 이 노트북이 문제없이 실행이 되는 것을 확인한 후에 제출하시기를 권장합니다. 심사위원들이 이제 코드를 쉽게 실행을 하고 또 여러분의 결과를 리플레이스를 하기 위해서 이 파일들만 제출하는 것은 저희는 권장하지 않고요. 이 경우에 또 마찬가지로 이 경우에도 이제 마찬가지로 디펜던시가 문제가 될 경우에는 코드 실행이 실패되면 채점하지 않습니다. 그렇기 때문에 반드시 도커 파일 형태 그리고 만약 이게 어려우면 주피터 노트북 형태로 제출을 하시기를 강력하게 권장합니다. 수상자 특전은 다음과 같습니다. 챌린지상은 각 문제별로 여러분이 푸신 정도에 따라서 저희가 그거에 대한 보상을 지급을 하는 상이고요. 각 문제별로 챌린지상을 받을 수 있으며 등급은 정답을 제출한 가장 높은 레벨에 따라서 결정이 됩니다. 레벨 1, 레벨 2, 레벨 3가 있고요. 각 문제별로 레벨 3까지가 준비가 되어 있습니다. 그래서 레벨 1은 10,000원, 레벨 2는 50,000원, 레벨 3는 100,000원 상당의 기프트 카드를 저희가 보내드릴 거고요. 예를 들어 문제 1은 레벨 1까지 풀었고 문제 2는 레벨 3까지 푸신 분은 레벨 1 보상이 하나 그리고 레벨 3에 대한 보상이 하나 제공이 될 거고요. 모든 문제를 레벨 2까지 푸신 분 같은 경우에는 3번까지 풀었다고 문제 1, 2, 3을 동등하게 레벨 2까지 푸신 분들은 레벨 2 보상을 3개를 받게 되십니다. 여기에다 추가로 탑 3 참가자 가장 성적이 좋았던 3명에 대해서는 대상 최우수상, 우수상을 수상할 계획이며 각각 이만큼의 부상을 받게 되실 것입니다. 이벤트 기간은 8월 31일에 이벤트 시작과 동시에 문제가 공지가 될 것이고요. 접수 및 참여 기간은 10월 4일까지입니다. 그래서 이 사이에 접수를 하시고 정답을 홈페이지에 제출을 해주시면 되겠습니다. 정답 공개는 10월 18일로 예정이 되어 있고요. 그때까지 접수 참여 기간 내내 매주 화요일마다 문제 Q&A 세션이 있을 것입니다. 이 세션에 대한 링크는 홈페이지를 참조해 주시기 바랍니다. 이로써 IonQ-Qcenter 퀀텀 챌린지에 대한 이벤트 소개를 마치겠습니다. 많은 참여, 많은 관심 부탁드리겠습니다. 감사합니다.
Okay. Okay, yeah. I guess I'll give a brief description of this problem it's about. So this problem mainly focuses on the variational quantum eigensolver. And so basically you need to try to use a quantum computer to simulate a chemical system or for example, like a molecule or materials using this algorithm called the variational quantum eigensolver, or VQE. So VQE is a well-known algorithm for near-term quantum computers. So what it does is that it's first it's designed a parameterized circuit. You can write it down as psi of theta. Theta are these unknown parameters. And then you optimize these parameters so that in the end you find the minimum of these energy functional. And then once you have found the minimum of this energy functional, you will find the best representation of the ground state or the low energy state of your chemical system, such as the molecules. So then, in particular, in this problem, we will consider this specific wave function ansatz called the unitary couple cluster with singles and doubles. It is defined in this way, in which we have like a phi here, which is a reference state, and then T1 and T2 are so-called cluster operators defined in these two equations. And then these two are these T1 and T2 are designed to be anti-Hermitian, so that once you exponentiate those, you got a unitary matrix, so that these unitary matrices can be implemented on the quantum computers. And then inside T1 and T2, you have this A dagger and A operator. These are fermionic creation and annihilation operators on one specific orbital. For example, A dagger A will be creating one electron in the orbital A, and the AI will be destroying one electron, annihilate one electron in the orbital I. And then so you can see this creates a single excitation in which one electron is removed from a certain orbital, and another one electron is created from another orbital. And then this one is a double excitation. And then each excitation is associated with a parameter here. So we have parameters for single excitation, we have parameters for double excitation. These are these unknown parameters that we want to tune and optimize so that the energy is minimized. All right, so now we have a overview of what VQE is and what we're going to implement for this particular problem. Let's go to task number 1. So so task number 1 is simplest task. So in order to implement these unitary couple cluster and singles and doubles, or UCCSD, on the quantum computer, you need to transform the creation annihilation operators into Pauli matrices. And then this can be done with the Jordan-Wigner transformation, JWT, so that your task is to transform these following two operators into these operators are written in creation annihilation operators, and then you need to transform these two into Pauli matrices representations. So we consider two examples. These two are both, you can see these two are both double excitations, but then these two are also slightly different. The difference is that in the first example, the first operator, these IJAB orbital indices are adjacent to each other. So we can consider a case of 1, 2, 3, and 4. And the second example, they are not adjacent to each other. And then you need to do the Jordan-Wigner transformation of these both of these operators, and then see what's the difference that you got in terms of quantum, in terms of the Pauli matrices that you obtained after you do the Jordan-Wigner transformation. So once you have finished that, we go to task number 2. So then, since we have these two operators transformed to Pauli matrices, we can implement that on a quantum computer. So you need to implement the circuit that you need to like write down the circuit that implement these operators. Okay, so I think there's a problem. This one needs to be exponentiated. So it's not like TIJB multiplied by that. It's actually the exponentiation of this guy. Can we modify that?
Sure, you can. We can do it later. Yeah,
Okay.
we will update the. Yeah, I think I don't do it, but yeah, could you update the Google documents and send it to me, the link?
I will fix that right now.
Okay.
Okay, yeah. Let's now go to task number 3. So that's once you implement the circuit, this operator, and then you will see that the circuit that you have will probably contains a lot of entangling gates, such as control NOT gates. So in the NISQ area, the entangling gates actually give you the most of the errors on the quantum computer. So that it is very crucial to find ways to optimize the circuit so that the number of entangling gates are minimized. So like the task you need to do is to optimize your circuit to cancel as many as entangling gates as possible, and then see what's the minimum number of entangling gates you can get, and then report the circuit the most optimized circuit that you got. Okay, so once you do that, once you have the most optimized circuit, you need to measure the energies in order to optimize the circuit parameters. Now, let's consider the simplest molecule for the H2 molecule in the minimal basis, the STO3G basis set. And then using the Jordan-Wigner transformation, write down its Hamiltonian in terms of Pauli matrices. So its Hamiltonian originally is written in terms of creation and annihilation operators. You need to transform that into using the Jordan-Wigner transformation to Pauli matrices. Okay, so once you have done that, now what you need to do is to implement the quantum circuit that measures the energy. And then because there are many terms in the Hamiltonian, you may need more than one circuit to measure the energy. So the first question is, how many circuits do you need, and why you need these many circuits? And the second one is, can you figure out ways to reduce number of circuits by measuring different terms simultaneously? To say if you can figure out ways that you can group terms so that they can be measured together in order to minimize the number of terms that you need to measure, so that to minimize the number of circuits you need to measure. All right, so that's task number. Let's go to the last task, which is the most difficult one. So that's in this case, like besides measuring the energy, we also measure the Hamiltonian matrix elements on the quantum computer, which is defined in this way. So we now have these two different quantum states that is obtained by applying these two different operators on the reference state. Okay, so now what this problem is that for a specific problem with 4 orbital 2 electrons, like the hydrogen problem, and then you need to set these two parameters Ti and Tj to be different so that these two states are not the same. And then we can choose like a specific term in the Hamiltonian XXXY. Your task is to first implement the quantum circuit that measures these particular Hamiltonian matrix elements for your own choice of Ti and Tj. You can choose arbitrary Ti and Pj as long as they're neither of them are 0, and then they're not the same. And then you test your you need to test your circuit by running it on a noise-free simulator to make sure you get the correct measurement of these Hamiltonian matrix elements. And then you also need to do some optimizations to reduce number of like entangling gates in your circuit. And once you do that, test your circuit on IonQ's quantum computers and discuss how the results compare with the simulator results. Okay, that's the description of the problem.
The second problem number 2 is about generative adversarial network problem. The generative adversarial network, so-called GAN, is one of the most promising applications in the machine learning world. What GAN does is it actually consists of two components, a generator and a discriminator, so that they are trained to fight against each other, and they resemble the distribution of the training data. And the classical GAN has been demonstrating very successful results, such as in human face regeneration, art paintings, and image translations. Due to the huge success in the classical GAN, people are trying to apply GAN into the quantum domain. But because of the limited resources, such as limited number of qubits in these devices, it's not easy or straightforward to apply GAN in the quantum domain. So problem 2.1 is first, you're going to design a GAN for small size images. So what you're going to do is you're going to design a GAN to generate MNIST handwritten images, 20 by 28. I posted a reference paper which shows one way of tackling these limitations of the resources. And what it does is it slices a single image into multiple small patches, and it consists of multiple quantum circuit-based generators, and each quantum circuit generator is responsible for constructing this small patch. And then they concatenate to make one image, and they train with classical discriminator. So that is how this paper is trained quantum-based GAN to generate an image. So in this diagram, as you can see, there are multiple generators, and each generator is responsible for a small patch of image, and they are eventually concatenated, and then they are trained with the classical discriminator. So in problem 2.1.1, describe how GAN would be trained and also describe its loss functions. The answer should include explanation about generator and discriminator later. Problem 2.1.2 is actually you going to design a GAN described in this paper and train it with just single digits 0. There are 10 digits from 0 to 9, but just train with a single digit 0. And the result of the GAN should be recognizable as 0. In problem 2.2, you are going to design and implement a quantum version of GAN that generates large size image, which is 256 by 256. This would be challenging, but also be very exciting. You are free to come up with an idea, your own idea, that can handle a large size image, as long as you consider the limits of current quantum hardware and resources. You may be able to get a hint from an example of the classical domain. For example, a conditional GAN provides a good baseline for this. One of the examples of a conditional GAN is pix-to-pix GAN, and the pix-to-pix GAN does image translation, such as you can see in the image bottom here, it converts a black outline image to a color image, or you can convert color image to a black outline image. You actually don't need to exactly follow the classical pix-to-pix algorithm I just described. You are free to choose any algorithm. For example, this variation of quantum GAN would convert a color back image into a black outline image. Or you can just design a GAN that generates a large size image without any input, just from a latent vector. As long as your GAN is able to generate a large size image, 256 by 256, you are fine. So in problem 2.2.1, first, describe how you would approach this problem for large size images with the limited number of qubits. Describe your logic and why you choose this way, why choose your way to tackle this problem. And in problem 2.2.2, first, explain the function of the GAN you are designing so I can understand your goal of design. And then design and implement and train it with a data set that has image size of 256 by 256. I posted some of the links for the data set that has a 256 by 256, but you are free to use other data sets. And submit your answer. And just like problem 2.1, please refer to guideline for submitting solutions so that we can reproduce your answer, your solution on my end without any problem. Thank you.